Hello viewers, I am Asghar Pasha, Assistant Professor, Department of Mathematics, MS Ramaya Institute of Technology, Bangalore. I am going to continue problems on differential equations solvable for x, and I am also discuss equations solvable for y in this session. Problem number 3, solve p cube minus 4xyp plus 8y square equals to 0 by solving for x. As you know, the method for solving differential equations which are solved for x is step 1, express equation in terms of x. Step number 2, differentiate that equation with respect to y and simplify to get an equation in terms of p and y only. Solve that equation and then get a relation in terms of p, eliminate p from that equation and the given differential equation. In this case, you can write the given differential equation as x equals to 4p cube plus 8y square divided by 4yp. X equals to p cube plus 8y square divided by 4yp. Differentiate 1 with respect to y. So LHS is dx by dy equals to quotient rule now, denominator 4yp into derivative of numerator. Numerator is p cube plus 8y square, derivative of p cube is 3p square into dp by dy plus derivative of 8y square is 16y minus numerator as it is p cube plus 8y square as it is numerator into derivative of denominator. Denominator is 4yp, so you have to use the product rule here. 4 into y, derivative of second function is dp by dy plus 4 into p, derivative of first function y is 1. So this is 4y dp by dy plus 4p divided by denominator square, which is 4yp the whole square. Now you write this dx by dy as 1 by p and simplify this to get 1 by p equals to 12yp cube dp by dy plus 64y square p minus 4p to the power of 4 minus 4yp cube into dp by dy minus 32y square p minus 32y cube into dp by dy divided by 16y square into p square. Cross multiply 16y square into p square and simplify this to get this equation, which is 8yp cube dp by dy plus 16y square p minus 4p to the power of 4 minus 32y cube into dp by dy equals to 0. Divide throughout by 4 to get this reduced equation. 2yp cube into dp by dy plus 4y square p minus p to the power of 4 minus 8y cube dp by dy equals to 0. Now you have to collect dp by dy terms. After multiplication and simplifying, you collect the dp by dy terms here. Dp by dy, when you take dp by dy common from first and fourth term, you get 2y times p cube minus 4y square into dp by dy plus remaining terms 4y square minus p cube into p equated to 0. You simplify this to arrive at this result. So p cube minus 4y square into 2y dp by dy minus p equals to 0. So we have two possible equations here. One is p cube minus 4y square equals to 0, which does not involve any derivative, which leads to singular solution. Another one, 2y into dp by dy minus p equals to 0, which has a derivative term and it leads to general solution. So as general solution is asked, let us take the second possible equation, 2y into dp by dy minus p equals to 0. Consider 2y into dp by dy minus p equals to 0. That implies 2y into dp by dy equals to p. You can solve this by variable separable technique. It is dy by p equals to dp by p equals to dy by 2y. Integrate it. Integration of 1 by p is log p, that is equals to half times integration of 1 by y is log y plus some constant of integration which is log c here. Use properties of logarithms and write half log y as log of y to the power of half, and again club these two to get log of y to the power of half into c. So p equals to c root y. So we have determined an expression for p. Now we have to eliminate this p from this equation and from the given differential equation. Substitute this p in the given differential equation. We get c cube into y to the power of 3 by 2 minus 4xy c into y to the power of half plus 8y square equals to 0. Simplify this. After dividing throughout by y root y, we get c cube minus 4cx plus 8 root y equals to 0. Take c common, then it is c into c square minus 4x equals to minus 8 root y. If you want, you can square it to get 64y equals to c square into c square minus 4x the whole square. This is the general solution of the given differential equation. Next problem. Problem number 4. Solve y equals to 2px plus y square into p cube by solving for x. Given differential equation is y equals to 2px plus y square p cube. You can convert this in terms of x equals to function of y and p as x equals to y minus y square p cube divided by 2p. Next, differentiate this equation with respect to y. Dx by dy equals to quotient rule here, u by v rule, denominator into derivative of numerator. This is derivative. Derivative of y is 1. Then use product rule for y square into p cube, which is minus 2y into p cube. When we keep p cube as constant and differentiate y square, and in the next stage when we keep y square as constant and differentiate p cube, it is 3p square into dp by dy, which gives this, minus numerator as it is, which is y minus y square into p cube into derivative of denominator. Denominator is 2p and derivative of 2p is 2 into dp by dy divided by denominator square, 2p the whole square. Now write this dx by dy as 1 by p, because you know that p is dy by dx. So 1 by p is dx by dy, and simplify this equation. To get 1 by p equals to 2p minus 4y into p to the power of 4 minus 6y square p cube into dp by dy minus 2y into dp by dy plus 2y square p cube into dp by dy divided by 4p square. Multiply throughout by 4p square to get this. 4p equals to 2p minus 4y p to the power of 4 minus 6y square p cube dp by dy minus 2y into dp by dy plus 2y square p cube equals to dp by dy. Simplify this. To get 2p, take 2p to LHS, 4p minus 2p is 2p, take all these terms to LHS. To get 2p plus 4y p to the power of 4 plus 4y square p cube into dp by dy, which is a combination of these two, plus 2y into dp by dy equals to 0. You can see I will group dp by dy term now. From the last two terms, from the third and fourth term, 2y into dp by dy is common. 2y into dp by dy into 1 plus 2y p cube, and this 2p plus 4y p to the power of 4 can be written as 2p times 1 plus 2y p cube. Now take 1 plus 2y p cube common to get this, 1 plus 2y p cube into 2p plus 2y into dp by dy equals to 0. Again we have two factors, one without the derivative term and the another one with the derivative dp by dy. The second one gives general solution and the first one gives singular solution. When you equate this to 0, 1 plus 2y p cube equal to 0, you get a singular solution. Consider the second one, 2p plus 2y into dp by dy equals to 0, as general solution is required. You write this as y dp by dy equals to minus p after transferring 2p to RHS, and then you solve this equation by separation of variables technique. Dp by p equals to minus dy by y, integrate it. Integration of 1 by p is log p, integration of 1 by y is log y with a negative sign, plus constant of integration log c. Use properties of logarithms and simplify it to get p equals to c by y. Now eliminate p from this equation and the given differential equation. Substitute p equals to c by y in the given differential equation to get y equals to 2c by y into x plus y square into c by y the whole cube, which is nothing but y equals to 2c x by y plus y square into c cube by y cube. You simplify this to arrive at this result, y square equals to 2c x plus c cube. This is the required general solution. Problem number 5. Obtain the general and singular solution of y square into log y equals to xpy plus p square. Now, you express given equation in terms of x. We can write it as xpy equals to y square log y minus p square. You transfer p square to the right side and then divide throughout by py to get x equals to y log y by p minus p by y. Equation number 1. Differentiate 1 with respect to y to get dx by dy equals to, for the first term, apply quotient rule, denominator into derivative of numerator. Denominator is p, derivative of numerator. Derivative of y log y is y into derivative of log y, which is 1 by y, plus log y into derivative of y is 1, minus numerator. Numerator is y log y into derivative of denominator, which is dp by dy, divided by denominator square, which is p square. This is derivative of first term, derivative of y log y by p, minus this is derivative of the second term, again quotient rule, denominator y into derivative of numerator dp by dy minus numerator p into derivative of denominator is 1 divided by y square. Now write dx by dy as 1 by p and simplify this to get 1 by p equals to 1 by p into 1 plus log y minus y log y by p square into dp by dy minus 1 by y into dp by dy plus p by y square. Now multiply 1 by p. 1 by p equals to 1 by p plus 1 by p into log y minus y log y by p square into dp by dy as it is, minus 1 by y dp by dy plus p by y square as it is. Cancel 1 by p, you will get 0 equals to 1 by p times log y minus other 3 terms as it is. Now group, you collect dp by dy terms and other terms as it is, you write, and then to get a common factor, you take p by y common here. When you take p by y common, it becomes y log y by p square plus 1 by y minus second term as it is y log y by p square plus 1 by y into dp by dy equals to 0. So in these two terms, y log y by p square plus 1 by b is common. So after taking common terms, we get y log y by p square plus 1 by y into p by y minus dp by dy equals to 0. We have two factors here. One is y log y by p square plus 1 by y, which involves no derivative and hence it leads to singular solution. The second one is p by y minus dp by dy equals to 0, a term involving derivative, which leads to general solution. So for general solution, consider the second term, p by y minus dp by dy equated to 0, which can be written as dp by dy equals to p by y. You solve this by variable separable technique to get solution as p equals to y by c. We have to eliminate p from the given differential equation and the equation p equals to y by c. Substitute this in the given differential equation. Given differential equation is y square log y equals to xy into the p value xy into p plus p square. Y square log y equals to xy into p plus p square, which implies y square log y equals to xy square by c plus y square by c square. Multiply throughout by c square to get c square y square into log y equals to cxy square plus y square. So the general solution of the given differential equation is c square log y equals to cx plus 1. Now, as singular solution is required, there are two techniques to find singular solution of the differential equation. One, we can start with the general solution, or else we can take the another factor free from the derivative term. Suppose if we take the general solution, c square into log y equals to cx plus 1, we can get singular solution from this. We have to differentiate this general solution with respect to the arbitrary constant c, assuming other two variables as constants. So if we differentiate 2 partially with respect to c, we get derivative of c square as 2c, log y is treated as constant, equals to derivative of cx is x and derivative of 1 is 0. With this, c becomes x divided by 2 log y. Now substitute this value of c in equation number 2 in the general solution to get c square log y equals to cx plus 1. This is equation number 2. C square log y equal to cx plus 1. C square log y equal to cx plus 1 is equation number 2. It is general solution. In this equation, we have to substitute c as x by 2 log y. So if you replace c by x by 2 log y, we get x square divided by 4 into log y the whole square into log y equals to c value x by 2 log y into x plus 1. So it is x square divided by 4 log y equals to x square divided by 2 log y plus 1. After simplification, we get x square plus 4 log y equals to 0 as singular solution of the given differential equation. Now method 2. Method 2 to get singular solution is through the other factor. As you have seen, the other factor was y into log y divided by p square plus 1 by y equated to 0. It's a factor free from derivatives. Now simplify this. It's y into log y divided by p square equals to minus 1 by y, or else y square into log y equals to minus p square. Therefore, p square is minus y square into log y. This is p square value. Now, consider the given differential equation. Given differential equation is y square into log y equals to x into p into y plus p square. This is given differential equation. We have to eliminate p here. So we have p square value, p square equals to minus y square into log y. We have to substitute this in the given differential equation. So one way of doing this is converting p or expressing this as an equation involving only even powers of p, which is easy because I have a value for p square here. For that, I'll shift this p to LHS, that is equals to x into p into y. I have to eliminate this p. If we square it on both the sides, we get y to the power of 4 into log y the whole square plus p to the power of 4 minus 2ab 2y square p square into log y equals to x p square y square, x square p square y square. So everywhere I have even powers of p to the power of 4 here, p square here and p square here. So just replace p square by minus y square into log y. First term as it is, y to the power of 4 into log y the whole square plus, now in place of p to the power of 4, p to the power of 4, p square is minus y square log y, so p to the power of 4 is y to the power of 4 into log y the whole square. Next, minus, I'll write this as it is, 2y square. Now in place of p square, I'll write this, p square is minus y square into log y, and right hand side equals to right hand side is x square into p square value. P square is minus y square into log y into y square as it is. Okay. So what I have done, from the second factor I got p square equals to minus y square into log y. To get singular solution, I had to remove this p, eliminate p from the given differential equation. But my equation contained only both odd and even powers of p. So for simplicity, I converted this equation involving only even powers of p. And then I replaced p square by minus y square into log y to get that equation. Now I have to simplify this. Okay, consider. We have y to the power of 4 log y whole square plus y to the power of 4 log y whole square, which is 2 times y to the power of 4 log y the whole square plus minus 2y square minus y square log y, again it is plus 2y to the power of 4 log y plus 4y to the power of 4 into log y equals to RHS minus x square y to the power of 4 into log y. Now, divide throughout by y to the power of 4 into log y to get 2 into log y plus I am dividing by y to the power of 4 log y, so it is only 4 equals to minus x square. Now simplify this. This is x square plus 2 log y equals to 4. So basically you can get singular solution in two different ways. One, by differentiating the general solution with respect to arbitrary constant, treating x and y as constant and then substituting the c value in the general solution, or else you consider the other factor which is free from derivatives. From that you get p value, substitute that p value in the given differential equation and arrive at a relation involving only x and y with no arbitrary constant as given here, x square plus 2 log y equals to 4. So basically this is the technique. There are two ways of getting singular solution. Now problem number 6. Obtain the general solution of p equals to tan of x minus p divided by 1 plus p square. First step, as you have to express this as x equals to function of y and p, you take a tan inverse on both the sides to get tan inverse p equals to x minus p divided by 1 plus p square. So with this we get x equals to p by 1 plus p square plus tan inverse of p. So it is in the form of x equals to f of y by p, standard form. Now differentiate this equation with respect to y to get dx by dy equals to, apply quotient rule, denominator into derivative of numerator minus numerator into derivative of denominator. Derivative of 1 plus p square is 2p into dp by dy divided by denominator square, which is 1 plus p square the whole square, plus derivative of tan inverse of p. Derivative of tan inverse of x is 1 by 1 plus x square. So derivative of tan inverse of p is 1 by 1 plus p square into integral differentiation dp by dy. Now write dx by dy as 1 by p and simplify this. 1 by p equals to 1 by p square into dp by dy minus 2p square into dp by dy plus 1 plus p square into dp by dy divided by 1 plus p square the whole square. Simplify this. 1 by p equals to multiply by dp by dy. dp by dy into 1 is dp by dy plus p square into dp by dy minus 2p square dp by dy plus multiply dp by dy into 1 plus p square into dp by dy divided by 1 plus p square the whole square. Okay. Now you simplify this equation. You can see here you have 1 p square dp by dy, another p square dp by dy, which makes it 2p square dp by dy plus 2p square dp by dy and minus 2p square dp by dy is 0. So you are left with the dp by dy and one more dp by dy. So it is 2 dp by dy. 1 by p equals to 2 dp by dy divided by 1 plus p square the whole square. You separate it to get 1 plus p square the whole square divided by p equals to 2 into dp by dy. Now solve this equation using variable separable technique. When we separate it, we get dy as 2p dp divided by 1 plus p square the whole square. So variables are separated here. Now integrate it to get y equals to, of course, RHS we need substitution. LHS is y, RHS, to integrate RHS put 1 plus p square as t. When 1 plus p square is t, 2p into dp becomes dt. So make that substitution in the integral to get integral of dy equals to integral of dt by t square. Now integrate it, y equals to integration of 1 by t square is minus 1 by t plus some constant of integration, and you simplify this to get y equals to minus 1 divided by 1 plus p square plus c. Now you can see here y is in terms of p, y equals to minus 1 divided by 1 plus p square plus c. And the given differential equation is p equals to, or else from 1 you can see it is x equals to p by 1 plus p square plus tan inverse of p. So from 1 and from 2 you can see elimination of p is not that easy. We cannot easily eliminate p to get a relation in terms of x and y explicitly. So this is x, equation number 1, x in terms of p. Equation number 2 is y in terms of p. So these two together constitutes general solution of the differential equation with p as parameter. So it's a parametric form, x in terms of p and c, y in terms of p and c. So we can stop here. This is a solution with p being parameter. You need not always express y in terms of x. In some cases you end up getting y as a function of p which cannot be eliminated from the given differential equation. In such cases you express x as p and c and y as p and c. Those two equations together constitute general solution of the given differential equation. Now type 3, equations solvable for y. And the procedure in this technique is similar to the procedure of equations solvable for x. As usual, if it is solvable for y, then you can express the given differential equation as y equals to, means y in terms of x and p. Now differentiate this equation with respect to x to get dy by dx equals to some arbitrary function of x, p and dp by dx. So replace dy by dx by p to get an equation involving p and x. So you'll get first order differential equation with variables p and x. Solve this equation to get a solution in terms of p and x. So equation of that equation, equation number 2, is a relationship between x, p involving one arbitrary constant, because we treat this as a differential equation of first order, dp by dx. So its solution is of the form g of x p comma c equals to 0. Now we have to eliminate p from this equation in the given differential equation. And as I mentioned earlier, if p cannot be eliminated easily, then we have to solve equations 1 and 3 for x and y to get x and y in terms of p and c. So in the parametric form, assuming p as a parameter. Let us take few examples. Example number 1, solve y equals to 2px minus p square by solving for y. You convert this equation in terms of y equals to 2px minus p square. Now differentiate this. Derivative of y is dy by dx equals to derivative of 2px. Apply product rule. 2p into derivative of x is 1 plus 2x into derivative of p is dp by dx minus derivative of p square is 2p into dp by dx. Write dy by dx as p equals to 2p plus 2x into dp by dx minus 2p by dx as it is. You simplify this to get 2p minus p plus 2x into dp by dx minus 2p into dp by dx equals to 0. After simplifications, you get p plus 2 into x minus p into dp by dx equals to 0. Multiply by dx by dp to transform this into a standard form, because it's not easy to separate the variables here. I'll try to convert this into Leibniz form. So to do that, I am multiplying throughout by dx by dp. With this equation becomes p into dx by dp plus 2 into x minus p into 1 equals to 0. So it is dx by dp plus 2 by p into x equals to 2. It is of the form dx by dy plus some function of y into x equals to some function of y. This is Leibniz's linear equation. You can find its solution by finding integrating factor. Integrating factor is e to the power of integration of p of y into dy, and then its solution is dependent variable into integrating factor equals to integration of right hand side into integrating factor with respect to independent variable plus some constant c. Now let us solve this. As I mentioned, its solution is x into integrating factor equals to integration of 2 times integrating factor into dp plus c, where integrating factor is the coefficient of x. P is coefficient of x, which is 2 by p. You have to integrate it. Integrating factor is e to the power of integration of 2 by p into dp. Integration of 1 by p is log p, so it is e to the power of 2 into log p. 2 log p is e to the power of log of p square, and you know that e to the power of log of f of x is f of x, so you get p square here. So the solution is x into integrating factor, which is p square, equals to integration of 2p square dp plus c. Now integrate p square. Integral of p square is p cube by 3. After integration you get xp square equals to 2p cube by 3 plus c. Divide by p square to get x as 2p by 3 plus c into p to the power of minus 2. So I have expressed x in terms of p. Now if I substitute this x in the given differential equation, I will get y in terms of p as y equals to p square by 3 plus 2c by p. You can see here equations 2 and 3 are in terms of parameter p. So these two together constitutes general solution of the given differential equation, as I mentioned earlier. Problem number 2. Solve y equals to 3x plus log p by solving for y. Given differential equation is y equals to 3x plus log b. Differentiate this with respect to x to get dy by dx equals to 3. Derivative of 3x is 3 plus derivative of log p is 1 by p into dp by dx. Write dy by dx as p equals to 3 plus 1 by p into dp by dx. Shift p to LHS to get p minus 3 equals to 1 by p into dp by dx. Now separate the variables. Dx equals to dp by p into p minus 3. Now integrate it. X equals to integration of dp by p into p minus 3 plus c. Now you resolve this using the technique of partial fractions. You have p into p minus 3 linear factors. One by p into p minus 3. There are many ways of resolving this into partial fractions. The elementary one is, for this linear factor, associate one constant a by p. For another linear constant, associate one more constant b. So it is a by p plus b by p minus 3. Take LCM to get 1 equals to a into p minus 3 plus b into p. Now put p equals to 0 to get 1 equals to minus 3a plus 0. So a equals to minus 1 by 3. This is a. Now put p equals to 3, that is equate other factor to 0, p minus 3 to 0 to get p equals to 3. You get 1 equals to 0 plus 3 into b, therefore b is 1 by 3. So basically what we have, in place of a we have a minus 1 by 3, and in place of b we have plus 1 by 3. This is one technique. Technique number 2. You know that 1 by x into x minus 1, it can be written as 1 by x minus 1 divided by x minus 1. Because when you simplify this, this becomes x into x minus 1, x minus 1 here minus x here. So x minus x 0, so it is minus 1 by x into x minus 1. Now this is for x plus 1. If it is x plus 1, I can do that. Okay. What is the other technique? Other shortcut method is 1 by p into p minus 3, straightforward. Equate this to 0, p equals to 0, substitute p equals to 0 everywhere except in this factor, so you will get minus 3 here, plus equate second factor to 0, p minus 3 equal to 0 gives p equals to 3, substitute p equals to 3 everywhere but not from the factor from which it is obtained. So when I substitute p as 3, I will get 3 here, 3 into p minus 3. So as explained here, a is 1 by minus 1 by 3 and b is 1 by 3. So you can easily write this in one step. 1 by p into p minus 3 equals to minus 1 by 3 divided by p plus 1 divided by 3 into p minus 3. But this rule is applicable only if denominator of a proper fraction contains non-repeated linear factors, no p square, no p cube, no p minus 3 whole square. Only if it is non-repeated linear factor, p is a non-repeated linear factor, p minus 3 is a non-repeated linear factor. In such cases, we can directly write its partial fraction as minus 1 by 3 by p. Of course, equate first factor to 0 and substitute that value everywhere except from the factor it is obtained. Equate the second factor to 0, substitute that value of p everywhere except from which it is obtained to get partial fractions of that proper fraction. Same thing here. We have a dp by p into p minus 3 plus p. So when we resolve this into partial fractions, we get minus 1 by 3 divided by p plus 1 by 3 divided by p minus 3 into dp plus c after resolving this into partial fractions. Now integrate it. Integration of 1 by p is log p and integration of 1 by p minus 3 is log of p minus 3 plus c. So I have expressed x in terms of p. Therefore x equals to minus 1 by 3 into log p minus log of p minus 3 plus c. Use properties of logarithms. Log a minus log b is log of a by b. So log p minus log of p minus 3 can be written as log of p divided by p minus 3 plus c. So x is, okay, if I take this negative side inside, minus log x is log of 1 by x, so we will get reciprocal of that, log of p minus 3 divided by p. So x equals to 1 by 3 times log of p minus 3 divided by p plus c. Multiply by 3 throughout to get log of p minus 3 divided by p as 3x minus 3c. And you know that when log x equals to a or log a equals to x, so by default base is e here, which means a is e to the power of x. So log of p minus 3 by p is 3x minus 3c, which implies p minus 3 divided by p is e to the power of 3x minus 3c. Now simplify this for p to arrive at the result p equals to 3 divided by 1 minus e to the power of 3x into e to the power of minus 3c. Now substitute this value of p in the given differential equation to get y equals to 3x plus log of 3 divided by 1 minus e to the power of 3x into e to the power of minus 3c, which is the required general solution of given differential equation. Problem number 3. Obtain the general solution of y equals to x plus 2 into tan inverse of p. Convert this, of course it is directly in terms of y is x plus 2 into tan inverse of p. You differentiate this with respect to x to get dy by dx equals to derivative of x is 1 plus 2 into derivative of tan inverse of p is 1 divided by 1 plus x square, derivative of tan inverse of x. So derivative of tan inverse of p is 1 divided by 1 plus p square into internal differentiation of p is dp by dx. Next write dy by dx as p to get p equals to 1 plus 2 divided by 1 plus p square into dp by dx. Now p minus 1 equals to 2 divided by 1 plus p square into dp by dx. You solve this using variable separable form. You separate the variables. You get 2 dx equals to 2 divided by p minus 1 into 1 plus p square into dp. Again you have to integrate it and you have to resolve this into partial fractions, but you can see here you have one linear factor p minus 1 and one quadratic factor 1 plus p square. How to resolve this? You are familiar with the method of resolving a proper fraction into partial fractions. We have 1 divided by p minus 1, one linear factor and one quadratic factor. This is equals to, it is a divided by p minus 1 plus, for this quadratic factor, bp plus 1 divided by 1 plus p square. Take LCM and simplify this to get 1 equals to a into 1 plus p square. Okay, it's not bp plus 1, it's one more constant, it's a bp plus c. We have to find 3 constants here, a, b and c. So when you take LCM, you will get 1 as a into 1 plus p square plus bp plus c into p minus 1. You can get one value directly by equating p as 1. If you substitute p equals to 1, then you get 1 equals to a into 1 plus p square, which is 1 plus 1, and this part is 0, so a is 1 divided by 2. Next, we have 1 plus p square here. You can give arbitrary value for p to get b and c, or else you multiply and equate the coefficients of like powers of p on both the sides. One equals to, now multiply, a into 1 is a plus a into p square plus bp into p is bp square minus bp into 1 is bp plus cp minus c. Now I'll group p square terms. 1 equals to p square into a plus b minus I'll group p terms. P is c minus b, and I'll group constant terms a minus c. Now you equate like powers of p. Coefficient of p square is 0 here, so we get 0 equals to a plus b, and coefficient of p is c minus b, equated to 0 because there is no p term here. C minus b equal to 0, and a minus c is 1. So like this you find the values of a, b and c. So as shown here, after finding a, b, c, a is 1 by 2, you can see 1 by 2 into 1 by p minus 1 minus b is minus half, c is also minus half. So we have got this. Now integrate it to get x equals to log of p minus 1 minus half into log of 1 plus p square minus tan inverse of p. So it is in terms of p. So this is the general solution, because x in terms of p, y is in terms of p. This is general solution of the given differential equation. So with this I will finish today's session. In the next session I will solve some more problems on equations solvable for y. Thank you.